Hello and welcome to Metal Reps. I'm Fish.
And I'm Ben. Today, we're talking about nuclear. Specifically, today we're talking about nuclear fission and fission reactors as a means to power generation and electricity. So this is extremely fun for me. I'm a physics guy. We're not going to be talking too much about bombs today, but we'll get into it a little bit, I'm sure. Yeah, we're talking about fission this week. Next episode, we're going to be talking about fusion. So two sides of the same coin, but very, very, very different things, in fact. So, yeah, let's get into it.
Yeah, so I actually was really surprised at how much I really fell in love with this topic. Partly because I've been reading this little book here. I by no means have read this cover to cover. This is kind of not that kind of book. But How to Drive a Nuclear Reactor by, who's this by? Colin Tucker.
Who am I reading?
Who's this reading? Yeah. This is a really cool book. If you have any sort of passive interest in modern nuclear engineering, but don't want to buy a $300 textbook, this is a really good way to get into it. It's a very...
Academic textbooks are freaking expensive.
No, dude. So the cool thing he does is he lays it out kind of like a traditional book. He kind of goes through the process start to finish in a very kind of literary, accessible way. So not too much technical jargon. Does get into a lot of physics, which we're going to talk a little bit about physics today. But
kind of unavoidable in this.
Right.
Topic.
We were talking about it the other day. It was how I was saying that when talking about nuclear fission, what I was mainly interested in is the kind of reactor operation. And it's not that I don't like the physics, because in order to even understand the operation, you have to understand at least a surface level understanding of the physics. So that's really what this book does really well. It kind of gives you a baseline of the physics and then uses that to move into how does a reactor actually work. And that's kind of what we're going to do today. So let's start with some stuff here. Before we get there, though, I did want to kind of mention, and we talked about this a little bit, I think it was yesterday, general energy production, kind of large-scale energy production, nuclear does not make up much of that at all.
No.
I think we said like 9 or
10%.
That's what I read, 9 or 10%.
I think it's more in the U.S., like 18 to 20% of the U.S. France, it's the vast majority of their energy production. Other places, it's little to none. Mm-hmm. So it's pretty fragmented across the world at the moment.
I wonder, this is more of just a general question here, but is it on the decline or on the rise, you think?
Oh, rise.
Is it on the rise? Yeah.
Yeah, especially with the investments that specifically fission, I think, is on the rise. I think fission is ever more on the rise, sort of as a byproduct of the hype of fusion in the sort of social space right now.
Gotcha.
Because people are just, at least from my point of view, I think the social, like, odious response to nuclear is sort of waning. At least I hope it is. I think people are starting to understand more that our need for very low emissions energy production is more necessary than our, honestly, like, parochial views of nuclear.
Right.
So,
and we're gonna towards the end of the episode, we're gonna talk about kind of the public perception of nuclear, specifically as it relates to nuclear disasters, but also bombs or another things, nuclear weaponry. But yeah, so nuclear does not make up much in the grand scheme of global energy production. Actually, mostly it's going to come down to coal and gas. So
which blows.
Yeah, coal. This is the percentage I found. So coal at 34% and gas at 22%. Which is, I mean, that right there is about half.
Yeah, that's half of, is that global?
Yeah, global.
Yeah, that's half of our world is run by stuff that is cooking our atmosphere.
Yeah.
Which is nuts.
But so
we need to get some nuclear powered fucking engines, cars.
That'd be sick.
Dude, how cool would
Dude,
a
that'd be so
nuclear car
sick.
be?
And I bet you it'd be really freaking good if it didn't do something stupid.
I bet you'd be really good if it wasn't really bad.
Well, here's the thing, and we're going to get into reactor operation, but what are you going to be driving your car and also trying to control, like...
Dude, imagine, okay, I'm jumping ahead here. We'll get into what I'm talking about in a sec, but Fish will understand this, and that's all I care about right now. Imagine looking at your speedometer and trying to adjust a moderator at the same time.
Yeah.
That'd be crazy.
That'd be insane. So I mentioned, get my notes back up here. So I mentioned coal and gas, and I actually wanted to bring those up up specifically because both coal and gas and nuclear all more or less produce energy in the same exact way. So what you're doing there is you're getting a heat source to heat water to make steam to turn a turbine. Yeah. Right? So
turn turbine equals electricity generation.
Exactly. So that's ultimately what's going on here. For all three of those energy sources, it's just the way that you do it is different. So with coal, I don't really know too much about the other energy production types, but coal, I imagine you're burning coal.
Fossil fuels.
Yeah, there you go. And then gas, you're igniting gas.
I mean, these are chemical reactions. These are not nuclear reactions. These are the reactions that happen, that the heat that releases when moving one chemical to another chemical, which in the form of like fossil fuels is burning a liquid into a gas, which generates heat. Thus the heat, moves turbines. So,
right.
Yeah. And nuclear is way better at doing that.
Well, let's get into nuclear then. So I threw this in here. We were just talking about before we started recording. I threw this in here not because I need to bring this up in order for anybody to understand how nuclear reactors work, but this is a question I had, so I'm just going to throw it in there. So when I was looking into how nuclear reactors work, you have neutrons flying around, which we'll get into here in a second. But my question was, hey, where do you start? Right. So this comes from Duke Energy. I'm just going to.
How do you turn on the on button?
Right. What is the on button for a nuclear reactor? So essentially, you use a neutron startup source. Specifically, they list californium 252 and plutonium 238.
I've never heard of californium. I don't even know what that is.
And so I still don't understand too much about this, other than these are going to be really energy dense and kind of just shooting, ready to burst essentially. Yeah. So what happens after they burst? And let's get into that. So,
and also, what does it even mean for a molecule to burst? So I would say let's start with what the structure of an atom actually is.
Yeah,
that's going to be helpful to understand what we even mean by neutron here. So an atom and how it is possible for everything to be made of atoms, but also be different things, is what's called the structure of the nucleus. So an atom is three main components. There is neutrons, there are protons, and then there are electrons. Those are the three things that make up an atom. The neutrons and the protons are really heavy particles. They clump up in the middle of the atom called the nucleus. And those two particles are surrounded by what's called electrons in orbital. And the important part to nuclear energy are specifically the neutrons of the nucleus. Those are the main part. But when we see something like californium 252, whatever the frick that is, and plutonium 238, these numbers 252 and 238, that's the number of neutrons. So if you see
is it the number of neutrons or the number of neutrons and protons? Combined.
It might be them combined.
I think it
might be them combined. Yeah. So there's the atomic number. If you see a element on a periodic table, there's usually in the top right-hand side of its like little element square in the periodic table, that number is the amount of protons in the nucleus. The amount of protons in the nucleus make up what type of atom it is. Like, if we are to, like a a hydrogen atom, its atomic number is 2.
Right.
Because it has 2 protons. But it also has 2 neutrons. That makes up the nucleus of a hydrogen atom. And then there's electrons around it in orbitals. But yeah, that's what we are talking about with this whole neutron business. And the reason it's called nuclear energy is because we are dipping our hands and stirring the nucleus of the atom.
Right. That is a good addition there. Okay, let me get back here. Okay, so we mentioned californium-252 and plutonium-238. So these metallic elements are inserted into the reactor with new reactor fuel as control rods. We'll get into what those are lifted from the reactor core. Neutrons from the neutron source start to fire, and because there's enough fuel for a sustained chain reaction, we start the fission process. So that's the new fuel is interacting with these neutrons firing from the neutron source. Okay. So the fuel that we're going to use, in the reactors that are relevant to today, there are different types of reactors that use different types of fuel. But we're going to be using a heavy nucleus like uranium-235. When uranium-235 absorbs a neutron, it briefly becomes an excited nucleus called uranium-236.
Excited meaning in a state of high energy and instability.
Yes.
So atoms are always looking to be in a lower energy state, and lower energy states are more stable, roughly speaking. So, but one thing that makes them stable is an even balance between the protons and the neutrons. So protons are positively charged, neutrons are negatively charged, and neutrons are neutral charge. It's literally in the name. They have no charge. Electrons are negatively charged. So for there to be an even this is the same thing. This is electromagnetism, right? This is the same thing as a magnet. You have 2 positively charged magnets. They want to run away from each other. If you have a positive, negative charge magnet, they suck, right? They stick to each other. It's no different at the subatomic level. So if you have an uneven amount of these different charged particles, things are going to get wonky. Some are going to get blasted off. There's another thing called the strong nuclear force, which is what holds the nucleus together, that can overpower electromagnetism. But roughly speaking, when something is excited, it is in a high energy, unbalanced state, and it wants to blow off some of its particles.
Which is exactly what happens. So in the case of
what on earth just happened?
Just happened. I think I just dropped a damn. Well, anyway, so in the case of uranium-236, it's incredibly unstable, and it splits into smaller fragments, and these are going to be called fission products. So again, that makes sense, the products of fission. So I when I originally made these notes, I had a graph in here. I ended up deleting it because you didn't actually need to see it to really understand this. But it was really funny. So there are 2 main atomic masses that will generally be split into. I don't know if you looked at much of the graph that I had on here, but no. I think it's 135 is one atomic number that generally these fission fragments are going to split into, and I don't remember the other one. I think it's like 50 something or 60 something. So what happens is when it absorbs a neutron and it splits, it is more likely to split into nuclei of these atomic numbers, if that makes sense. And we'll get into one of those. But what was really funny is I guess there's a joke in the nuclear industry. They call this nuclear fission yield, product yield, something like that. They call this graph the Dolly Parton curve.
What?
Which I don't know if you know who Dolly Parton is.
No.
An actress with very massive tits.
Oh!
and
I don't care the reason. It's a good name.
And the reason they call it, this is hilarious, and I really wanted to bring this up because it's so funny to me. And the reason they call it the Dolly Parton curve is because if you look at a graph, those 2 atomic numbers, the probability goes up. So the graph looks like a pair of tits.
Hey, okay, it's a tits graph.
Yeah.
Dolly Parton curve. That is outstanding.
Yeah.
Might as well call it the freaking somebody else with the enormous tits curve.
Just take your pick, really.
You see someone on the street, that's the curve.
That's right. That's right. So I mentioned one side of that fission product yield graph is going to be around 135. So that means one common fission product is going to be xenon 135 with an atomic mass of 135. And we're going to talk a little bit about that later because that is very important for reactors. But before we get there, right after fission, so we got your fission products. Right after that happens, you also have what's called prompt neutrons. Prompt neutrons kind of fly out of the this whole thing that just happened here. This whole, not explosion, but this.
I mean, it on a subatomic level, it kind of is.
You have prompt neutrons, and now there's generally going to be 2 to 3 of these. I think the average is like 2.4, generally average. So 2 to 3 neutrons are going to fly out of the whole deal there. And what they're trying to do, not trying to do anything, but what they're going to do is they're going to interact with more uranium-235 and to repeat this process over and over again. That is what's called a chain reaction. If the amount of fission events that are occurring supply enough neutrons to further create more fission events with more reactor fuel, you have what's called a chain reaction.
So, the way you might wonder, like, okay, what does this have to do with creating energy? And so this stems back to one of my favorite people in history, Albert Einstein.
Smart dude.
So when a neutron enters the nucleus of a uranium-235 atom, causing it to be unstable, an unstable isotope that is uranium-236, causing it to blast apart. And by the way, this happens in much, 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 much shorter amount of time than humans could ever perceive. Like it's fractions on fractions on fractions of a second. So when that happens, you don't get a perfect, even amount of however many protons, neutrons, and electrons were in the uranium-235 atom, just split apart. It's not a perfect conversion. So some of those particles disappear. And you might ask, well, where the frick did they go? Right? That they got converted into energy. So that's where Einstein's E equals MC squared comes into play, is energy is equal to mass times the speed of light squared. Mass and energy are interchangeable, right? We can't convert energy into mass, but, well, can we? I don't actually know if that's true or not, but we definitely can convert mass into energy. So some of these particles, quote unquote, disappear. They don't actually disappear. They just get converted into energy. That energy is what we use for our energy production. So the reaction of mass, the loss of mass when splitting the uranium atom gets converted into energy. And that's why, which generates more neutrons, which hit more uranium-235 atoms, which causes more to split, losing mass, creating more energy, and so forth. That's how energy is actually created, is because we are literally turning mass, turning weight into energy.
Right. And then energy also, you could say, heat.
Right, which is to say heat. Yeah, same thing.
Which will matter later, and we're going to go over that. So we have defined what is happening more or less in fission, and then how fission can result in a chain reaction of more fissions, should you have enough fuel in a close enough range so that the neutrons can fission with them. Now, let's define some terms here, because this first one is actually a really important term. So you'll hear people talk about nuclear energy and kind of in like the Hollywood sense, and they'll say, oh, it's going critical. It's going critical.
That usually means a bad thing.
It usually means a bad thing. Well, it doesn't actually mean a bad thing. So essentially all criticality is just what I said. If you have enough neutrons, prompt neutrons coming out of the fission event that are enough to supply neutrons for a further fission event, you are critical. And if that ratio is kind of stable, and you don't have too many neutrons or not enough neutrons, you are critical. Then supercritical would be you have too many neutrons, and then subcritical you'd have not enough.
Right.
And then reactivity is another term here. Reactivity is just a way to describe kind of what is happening in relation to criticality. So the term it's a term expressing the departure of a reactor system from criticality. A positive reactivity addition indicates a move towards supercriticality power increase, and a negative reactivity addition indicates a move towards subcriticality power decrease, which is basically what I just said. Does that make sense?
Yeah, when I think of critical, I think of like a Hollywood movie in the world of like a power plant. When I see critical, I think of critical red flashing, blinking on a screen. Something's about to blow the frick up.
Yeah, which is
this is not that critical.
The irony is that you'll have those blinking red lights with anything other than criticality.
Right. Yeah.
Right.
Yeah.
Criticality is kind of what you're after.
That's what you want. You don't want, more or less, but overcritical,
Right.
supercritical, or subcritical. But yeah, that's. I don't know if we might talk about this later, but that's actually the biggest problem with fission reactors is you can't easily just turn them off. There's not an off button for a fission reaction.
Mm-hmm.
So,
well, kind of is, as far as like, well,
there's scramming, which we might.
we will talk about that. That's kind of what I was going for. That's about as good as you can get, I would imagine.
Right.
As far as stopping reactions or the ability to react. But we will get there. Okay, so I mentioned before, I don't remember when I mentioned that. Right, so the one of the common fission products is going to be xenon 135. And fun fact for you about xenon 135, I didn't know this until I started researching this, and actually relatively recently I didn't know this. It's actually the strongest neutron absorber known.
Oh, really?
Yeah. So you got to think about this in terms of you have uranium-235 that wants to absorb a neutron, essentially. And then you also, in the same system, have xenon-135 that also wants to absorb a neutron and is even stronger than uranium-235. And is kind of pulling away, as far as a probability is concerned, kind of pulling away from uranium to be able to fission.
Xenon... So xenon captures neutrons better than uranium does.
Yeah.
And it in fact it encourages the capture more than interesting.
And this is and we'll get into it here in a little bit, but we'll get into it now. So as far as a reactor goes, if you have too much buildup of xenon, you will not have the neutrons available to fission for uranium.
Because xenon's eating them.
Yeah. And this is what we would refer to as xenon poisoning. So you can poison a reactor if you have...
How do you get rid of xenon?
So there are two ways to get rid of xenon. So unless there's more, and I'm not thinking of them. But there are essentially...
there's two unless there's not.
Yeah. So there's two ways to get rid of xenon. So xenon can just decay.
Yeah.
Where did I write that down here?
Does xenon have a half-life?
Of roughly 9.2 hours.
Okay, so that's when we say half-life, a half-life is not really a physics or science term. This is just a term to tell somebody this duration is how long half of whatever you started with will be there.
Yeah.
So, for example, caffeine has a half-life of like 4 to 6 hours. Yeah. When you drink 100 milligrams of caffeine, in 4 to 6 hours, it's dependent on your biology and the type of caffeine, but in 4 to 6 hours, 50 milligrams is still going to be inside of you. And 4 to 6 hours after that, 25 milligrams is still going to be inside of you. 4 to 6 hours after that, 12.5 milligrams is still going to... That's a half-life.
Yeah.
So technically, when you say it that way, it makes it sound like whatever the half-life of something is will extend into infinity because it's never going to hit zero. It's just going to keep cutting in half and half and half and half. That's not how it actually works. But roughly speaking, the half-life of any given particle is how long that duration is how long it will probably decay, when it will probably decay.
So xenon-135 can't decay. Good luck getting it to that point, though, because, like I said, it is such a strong neutron absorber that if there are neutrons in the system, they're going to find it. So more than likely, what's going to happen is xenon-135 is going to capture a neutron, become xenon-136, which is stable, and it does not have that absorption effect anymore. So it'll remain in the system until a 136 can decay, but it will no longer pose a threat as far as xenon poisoning is concerned.
So once xenon captures a neutron, it's effectively benign.
That's my understanding, yeah.
Huh, interesting. So, but how many xenon atoms after the decay of a uranium-236 atom are produced on average? Is it just 1-to-1 ratio? For a single uranium-236 decay equals, on average, 1 xenon-135?
I think that kind of makes sense in my brain.
Well, as far as molecular structure goes, 135 is pretty damn close to half of 236. So I don't know. I don't think it could decay into 2 xenon-135s.
Right. That's what I'm thinking.
Because there's not enough particles there. So if one uranium-236 atom decays into, let's say, 2 neutrons and also one it shoots off 2 neutrons and also decays into a xenon-135. That xenon-135 could absorb one of the 2 neutrons, let's say, from another equally split uranium-236 atom.
Mm-hmm.
Even then, you would still have the neutron that first caused the uranium to be unstable, and also the second neutron that was blasted out, even if the xenon absorbed one of the 2, and then it would become benign. So xenon sounds to me like it can't completely shut down it can't completely put a halt on the reaction.
Well, so, and we're going to get into this a little bit later, but that's kind of part of general reactor operation, is burning off xenon as you adjust power levels. Because if you just leave reactor power stable for a certain amount of time, you will just burn off the xenon. And when I say burn off, that's what I'm talking about, allowing enough time for a neutron to be captured by xenon and rendering it obsolete as far as the captures, the absorption system is concerned. Mm-hmm. So yeah, so that is just kind of part of the equation. It's just giving the xenon enough time to burn off out of the system.
Okay, gotcha.
Anywho, okay. So when we're talking about, Google's trying to talk to me.
Man just said any hoozle and it thought it said, hey, Google. Stupid phone.
So back to uranium-235. To kind of complicate the system further, we're talking about neutrons being captured by uranium-235 to start the fission process. Mm-hmm. Now, in specifically the types of reactors that we're talking about today, you can't have fast neutrons. So a fast neutron is going to be a neutron traveling at around 14,000 kilometers per second. Which is,
you can't outrun that one.
Which is really dang. What was that thing? You told me something. You told me a fun factoid about distances.
Well, 14,000 kilometers is a very significant portion of the United States.
Yeah. In a second.
In a second.
Yeah.
In a second. Yes. That's insane. Imagine going like freaking halfway across the United States in a second. This is how fast. Now, this is crazy. So neutrons are quick, but like subatomic particles can move fast. And the thing about neutrons is because they are of neutral charge, they are not attracted or repulsed by other atoms. They can shoot right through stuff and just go blast through unharmed, right? They're probably going to smash into an atom nucleus, eventually, because there's a lot of them. But if you also know, atoms are largely empty space. The nucleus is extremely tiny. So the nucleus to the electrons that are in orbitals around it is so if a nucleus was the size of the Earth, the electrons would roughly be about as far away as the sun. That's how much space there is between the nucleus of an atom and the electrons around it.
Yeah.
That's insane. That's what people mean by atoms are mostly empty space.
Yeah.
So if a neutron is flying past the United States at 14,000 kilometers a second, it is easy for that thing to just fly through walls and what you would think as the most hard structures imaginable. It's because these structures at the subatomic level are literally universes between them. So that's why something like a subatomic particle can just fly through anything so easily, is because there's not really much for it to hit. Eventually it will smash into a nucleus, right? But what's fascinating is even this fast neutron is just a pathetic fraction of the speed of light.
Right. Yeah. So those are fast neutrons, and that's a really interesting thing you just told me there. That's crazy. But as far as uranium-235 is concerned, it wants nothing to do with that fast neutron. It's not going to be able to absorb that. So you got to slow these suckers down to they call these thermal neutrons. So that's going to be about 2.2 kilometers per second. That's
nice and slow.
That's
nice and slow.
That's
2 kilometers per second.
That's still pretty dang fast, but that's a lot more manageable, I would say. And in
much greater chance that it's going to get captured by a uranium nucleus at that speed.
Right. So the natural next question is, how do we slow these suckers down?
Yeah.
Right.
Because as I just said, they can travel through almost anything at that speed.
So how do we slow these suckers down? If we are operating a nuclear reactor, we want fission to occur so we can have power output. So we got to slow these suckers down. So how are we going to do that? And to do that, let's talk about the reactor core. And specifically, we're going to look at a pressurized water reactor. So what is a pressurized water reactor? Well, it's a reactor that keeps its water under pressure.
Wow.
That's about...
Such a creative name.
That's about as simple. That's kind of hilarious because a lot of these reactor type names are very on the nose. We're also going to talk about boiling water reactors.
Yeah, you'll never guess what those reactors do.
Okay, so let's look at a PWR reactor core. So, and a lot of these are going to share similarities between their reactors. I'll highlight differences as we see them fit. But you're going to have fuel rods. So these are steel rods containing ceramic pellets made of uranium, enriched to about 3.5 to 5%. So not very much uranium.
So enriching means, so uranium, uranium-235 and uranium-238, those are the two isotopes of uranium that we're going to be talking about mostly, and 236, of course, the unstable version of 235. But uranium-238 in nature is 99% of the uranium out there. Right? So the problem is uranium-238 is not... It's way more stable than 235 and just infinitely more stable than 236. So the chances of a neutron hitting 238 and it causing it to, become unstable and blow out more neutrons is basically zero, as far as I understand. So in order to get this chain reaction, we need uranium-235, not 238. But the problem is there's basically none of that. So we get massive chunks of uranium I'm not exactly sure how this is done, but enriching it is basically just getting rid of the 238. The uranium-238 is isolating the uranium-235. And this 3.5 to 5% number is how much 235 uranium is in the uranium pile, as it were. So for a reactor to keep reacting well, the uranium enrichment needs to be at least 3.5 to 5% uranium-235, and the rest can be uranium-238.
Right. So that is, like I said, that is in little pellets. They look like they're like little pea-sized pellets that go into your reactor core in the form of your fuel rods. So those are lowered in like that.
Gotcha.
The other thing you're going to have in a reactor is a moderator. So this is what I was talking about with slowing down neutrons. So you need a substance to, again, moderate the speed of the neutron. So this is kind of elastic collisions. So this is, you're going to be hitting something that's going to take the energy out of it, and more or less. Now this can be a whole lot of substances. Modern reactors, specifically PWR reactors, are going to use water. And this is just light water. And now I actually didn't get a clear answer on this. I don't know if the water used as a moderator is actually the same water that is the coolant. That was what I didn't know that. I don't know if there was like a separate water location for moderator, or if the coolant.
I'm sure there is.
I couldn't figure it out, honestly.
So if somebody happens to own a reactor, let us tour it, please.
Well, that's the thing, is they won't let you.
Yeah, no, reactors are not public areas.
They're. I think I was starting to tell you a little bit about this, like a week ago, I think. But there is a reactor, an old reactor that's not in operation anymore, that you can tour out in. I want to say it's New Mexico, but that might be completely false. That I just lied to you. I think it's called EBR-1, and it's a breeder reactor.
It breeds.
It breeds.
Wow.
I believe it's for specifically creating plutonium. So that's what it does.
It's for creating the on switch.
Yeah.
For reactors. Interesting.
Right. But so you could tour that. They give you guides and stuff, and you can go through and see that. I'd love to do that. But as far as like just like a live nuclear reactor at a large scale facility, no, you're not getting in there without proper training and an actual real reason to be there, other than, ooh, that's cool.
Right. There's a channel called Smarter Every Day on YouTube.
I saw that. I saw those videos that you're about to talk about.
Right. And he actually has a video of him touring a nuclear reactor.
Yeah, but he's
also got millions of.
I was going to say, if you go,
he can make a real impact in the social sentiment towards nuclear power. Yeah,
I think if we went to a reactor and was like, hey, we got a podcast, we got 50 subscribers, we want to go.
Yeah, we wouldn't be able to make a difference.
This would be really good for our discussion on nuclear power.
Yeah.
I'd be like, nah, dude, we're busy.
Yeah.
So that's your moderator. It is there to slow down the neutrons so that fission can happen. I mentioned it before, but you also have coolant. This is in the case of PWR, and actually a lot of different reactors. There are some where this is not the case, but your coolant is also going to be water, and it is carrying heat away from the reactor core. Now, keep that in mind, because we're going to come back to that. So when fission occurs, we are creating 2 to 3 neutrons. Now, in a lot of cases, this might be too many neutrons for what you're trying to do. Maybe you're trying to lower overall reactor power, stabilize it, whatever you're trying to do. So in order to get a hold on what your reactor is doing as far as the fission output, you have something called control rods. So I mentioned xenon as a neutron absorber. So now what a control rod is, it can be lowered from by the reactor operator. It can be lowered into the core, and it is kind of, I don't know exactly how structurally it works, but it contains a neutron absorber in it, generally like boron or something like that, which is going to be a very, also not nearly as good as xenon, but a very good neutron absorber. So what you can do is you can say, hey, we're going to lower these into the reactor to take neutrons out of the equation. Does that make sense?
Yeah. Yeah, so I think neutrons can fly through stuff pretty easily because they're not positively or negatively charged, so they're not easily attracted to different types of atoms. But there is still materials like water that will slow them down, or in fact just suck them up, absorb them.
Right. And that's
if they're slow enough.
And water, this is an interesting little fact here too. Water can also absorb neutrons.
Yeah,
Mm-hmm.
Right.
It's that is kind of as far as the balance of reactor operation goes. That is something that has to be. It's not as significant as something like the intentionally put there boron, or especially not xenon, but it does play a role in neutron capture, as far as what they would call your neutron population. And that's simply just how many neutrons are existing in the system at a given time.
Yeah. So yeah, when neutrons are moving fast, if water is in fact a moderator to slow them down, one thing that does to the water is tremendously heats it up, because thanks to Einstein, we also know that the faster something is moving, the more mass and energy it has. So when something slows down, it's losing energy, but because the conservation of energy, that energy doesn't just disappear. In the case of neutrons, when they get slowed down, that energy gets absorbed by whatever is slowing it down, which in this case is the water. That's called kinetic energy. Mm-hmm. When the neutron is being slowed by the water, the heat that's being generated from the neutron slowing down gets absorbed into the water, heating the water up.
Exactly. So that's control rods. So the other two brief components that we're going to talk about are the general reactor vessel. So that's going to be, in the case of a pressurized water reactor, I believe your entire vessel is pressurized as well. So it kind of keeps the entire system under pressure. So there's that. And then you also have, this is more for safety, like environmental safety or the safety of the workers, you have a containment building, or a containment structure around the...
which didn't always used to be a thing.
Well, we're going to talk about here in a minute an example of when that wasn't the case. And that's really stupid. Yeah. So I don't know if I think actually, so the containment building, at least anymore, is built to withstand some pretty harsh treatment. So
isn't there this could be me pulling something straight out of my freaking ass, but okay. Isn't there a standard that they have to be able to withstand a plane flying into them because of 9/11?
I have this written down at the end. We're going to talk about quite a few things at the end, but I'll just kind of jump ahead real quick because I put this at the end here. So the containment kind of structure is built to withstand things like internal explosions, if you had something like that, steam pressure, and aircraft impact.
Yeah. Okay, yeah. Aircraft. I don't know where I heard that, but yeah, after the 9/11 attacks, in the case of somebody wanting to sabotage a place that could do a lot of damage, like a nuclear plant, they have to be able to withstand a plane terrorist attack by way of flying into the dang thing.
Yeah.
Which is kind of, that's not hilarious, but that's hilarious.
Absolutely hilarious.
Yeah.
Okay, so we mentioned the coolant getting heated. So this energy being created by fission kind of transferring its energy in the form of heat into the coolant, heating the water. This is the important transfer of energy that is going to ultimately get us our power production. So the coolant gets heated. Now you have really hot water. In the case of a pressurized water reactor, it stays. So the point of the pressure is so that it cannot boil under pressure. So the heated water, not boiling, travels out of the core in near a secondary loop of water, if that makes sense. So what this hot water is coming into, not mixing with, but coming into contact with this other water, heating it, and then that water goes into a steam separator, which is what that is ultimately doing is the water is boiling, the steam travels up, and any water droplets that are in the steam are separated out and then can be used back into the cooling process. And then the steam travels into the turbines and turns the turbines. So that's going to be
how you get electricity.
Yeah, so that's going to be a pressurized water reactor, how it converts coolant into steam through a secondary cooling loop.
Interesting. It's interesting that they also capture all the little excess water droplets in order to continue using it.
Yeah. And that's actually true.
Nothing goes to waste.
So we're going to ultimately talk about 3 different reactor designs today. That is true for, I believe, all 3 of them. They all use steam separators, I do believe.
Also, fun fact about pressurized water reactors. These did not exist until the Navy wanted a nuclear-powered submarine. And in order to make that happen, the pressurized water reactor was born.
I mean, hey, if we can have a nuclear-powered submarine, why can't we have a nuclear-powered car?
I mean, they're one and the same almost. Why not both?
They're vehicles.
Right. They are propulsed forward. What? Might as well do it. Yeah. Nuclear car.
That's what I'm saying. So I
might as well call it a cancer mobile.
I mean, maybe depending on
how unsafely you build your nuclear powered car engine.
I mean, if you've got enough, you'd have to have a pretty massive freaking car, and it's going to be heavy as all Christ. But if you've got enough concrete,
it's heavy as all Christ, but you can compensate with all the more horsepower, then what does it matter?
I suppose. I mean, you'd have to have just feet of concrete in front of you, but
or lead or something
like that. Yeah. So yeah, that's coolant as far as PWRs, and we're going to talk about the differences between different types of reactors when it comes to coolant. But one more thing about control rods before we move on to that. So I mentioned that control rods can be lowered into the system to kind of systematically remove neutrons from the population, and this can be used to decrease power or stabilize or whatever you need to do with it. But there is, if let's say there's a problem, there's a countless number of problems that could happen that you would need to do this. But so I won't get into anything specific, but there is kind of an emergency shut-off button for reactor. Shut off in air quotes here because it's not
right.
What it's doing is
shut off in the best way you can.
Right. What it's doing is if you hit this what's called a SCRAM button, you are going to immediately plunge all of the control rods into the reactor all at once, and you're going to essentially just zap all the neutrons from the population. And no neutrons means no fission, which means no chain reactions.
Right.
And that is how you turn off a reactor. So that's called SCRAM or reactor trip, which is very important and going to be very important coming up here in a little bit. So that is a pressurized water reactor. There is also what's called a boiling water reactor. Now, these are interesting. Pressurized water reactors, at least in the United States, are the most common type of reactor.
I think they're the most safe as well.
That's, as we're going to talk about, that's probably true. But boiling water reactors still are absolutely in production and being built. You talked about an advanced boiling water reactor.
Boiling water reactors are still being made. They are not just simply called boiling water reactors anymore. They're called advanced boiling water reactors, but they are still being made. I'm pretty sure PWRs are still head over heels more popular than them, though, as far as I understand.
I feel like that kind of makes sense, though. And here's why. We'll go into it. So the difference between a PWR and a BWR. So when I talked about PWRs, what I said was the coolant remains under pressure within the core, cannot boil, moves up and out, and heats a secondary cooling loop. That secondary cooling loop will boil and convert to steam. What a boiling water reactor does is the water is not under pressure, or at least not under as much pressure, and the the water is allowed to boil into steam within the reactor core itself. So think about this. You made a face.
That sounds, and I'm not smart enough to know specifically on a detailed basis why, but that sounds dangerous.
So what does this look like? So the water, as far as your coolant goes, whether that be feed water or this kind of recycled water that we were talking about through the steam separators, is kind of funneling through the bottom of the reactor and then up. And it, at some point in the reactor core chamber, is allowed to boil from within it. Now, what does this do? Well, this creates what's called voids. So what is a void?
Voids.
What is a void? Well, a void is
My ass.
You're right. You got your ass in a nuclear reactor. That's right.
That's my.
What a void is essentially just a void in the coolant. So a gap in the coolant. Why does that matter? Well,
How would a void occur? How would a gap in water? How does that make sense? How does a gap in water occur? I guess unless it's above the water.
how does a gap in water occur? Well, I'm trying to conceptualize this because I don't actually know how I kind of said this earlier. I don't really know how coolant travels through the reactor vessel. I don't know if it's through like a series of pipes or it's just kind of freestanding within the reactor vessel.
Surely there's like water pumps, and it's being air bubbles in a water pump is a pretty normal thing. So maybe it's just something as simple as that.
I think that's what it is, because when I've looked at diagrams, they almost make it seem like the entire vessel is submerged in water. Now that is the case for certain types of experimental reactors, but as far as large scale, I don't know how that works. I think suffice it to say, just for the sake of the discussion, just think of, you have coolant flowing through your system. There are pockets or places where, because of boiling, there is no coolant. And that's that's, well, in the case of a boiling water reactor, that's normal.
Oh,
that is.
Well, that sounds dangerous. I guess I don't know.
Well, so think about it this way. So you get these voids because temperature goes up and you boil water, which creates these voids.
Yeah.
Well, what you can do to balance that is you can just insert some control rods, remove neutrons from the equation. Less neutrons means less fission, which means less temperature, which means less boiling.
I suppose.
Yeah. Not that I'm arguing for
And also, I know I don't. Do you know the difference actually between a standard boiling water reactor and the more recent advanced boiling water reactors?
I know almost nothing about the new one.
Yeah. As far as I know, they're like relatively recent designs, and I don't know much about them.
Again, not that I'm saying all that because I'm an advocate of boiling water reactors by any means. I honestly don't know enough about the field in general to really have a preference. But I would agree with you in that pressurized water reactors sound safer.
I think they sound safer.
They just sound safer.
I mean, if we're running one in a submarine, like, clearly we can make this thing pretty freaking safe.
Yeah. Well, so we talked about how BWRs might be unsafe. I have no idea. But one thing that PWRs and BWRs have in common is they have what's called a negative void coefficient. What is a negative void coefficient? You and I talked about it, so I'm curious what you say here.
What it was. It was something. So we got a void. So a void. So negative is your chain reaction is on the downturn. Mm-hmm. And there's a void somewhere in that equation. And then coefficient, efficiency, but co.
Okay.
I have no idea what it means.
That's fair. This is one of those kind of more tough terms. So let's break it down by the word.
Why isn't this as simple as boiling water reactor?
Exactly. Yes, that is as simple as it needs to be. Okay, so let's break it down by each individual word here. So void, we kind of defined a void, a gap in coolant.
Yeah.
Let's just leave it at that. Fun.
What is happening? What is dropping?
This I'm putting it up here because I don't like how it falls down. I don't like how it lays down there, and then it'll fall off my lap and then hit the metal.
Okay.
And it's really annoying.
It is.
Well, it's not happening to you, so it shouldn't be that annoying.
Well, I'm hearing it in my freak.
Sick. All right.
Negative void coefficient. What is that?
Let me regain my composure here. Okay, so let's break it down by the words. So void, we understood what a void is. It's a gap in coolant. Negative, that's a pretty obvious word here. So in relation to something, something's going down, right? And the coefficient is, this is kind of a loose word.
Big word. I barely know what that means on its own.
It's also kind of a vague word too. So coefficient essentially just means in relation to a status, there is a change. Right?
Okay.
And in the case of a void coefficient, we're talking about reactivity. So reactivity is your status. So let me rephrase this phrase a little bit. Let me rephrase the phrase. So in the presence of voids,
yeah,
reactivity as a status goes negative.
Yeah.
And that's essentially what a negative void coefficient is.
Okay.
So think about it this way. So you've got BWRs and PWRs, which use water as a coolant, but also water as a moderator. We talked about that. Yeah. So what happens is when you're, and I guess this kind of answers my question from earlier on if coolant and moderators are the same exact thing as far as like
moderator and the cooling.
Not are they the same substance, but are they literally the same exact?
Is it the same pool of water that's doing the moderating and also the cooling?
And I think this kind of answers that question, if I'm being honest. So what happens is when your coolant boils away. In the case of a boiling water reactor, that happens because that's the design of it. In a pressurized water reactor, maybe you have a loss of pressure or something like that. Your coolant boils away and your moderation goes with it, right? So what does that mean? So,
which means your reactivity would go up. No,
it
would go down.
It would go down. Negative. Yeah. Okay, so it would go down because it's a negative void coefficient.
The moderator is increasing reactivity because it's slowing down the neutrons.
So let's just break it down for the folks, because the folks at home don't know what's happening. Let's break it down a little bit.
I don't know what's happening. I'm the folk at home.
I'm in my home right now.
And I don't know what's going on.
So the coolant boils away.
Yeah.
And with it, the moderator, because it's the same substance. And if you don't have a moderator, you can't slow down neutrons. Because that's what a moderator does. It slows down the neutrons. So if you can't slow down the neutrons, the likelihood of fission occurring for uranium-235 is very small.
Goes down.
Is minuscule, almost irrelevant.
Yeah.
Right? So now you've still got neutrons flying around your system, but they're not going to be doing much anything. Temperature's still going to go up because you're still smacking against the kind of the overall structure of your reactor.
Right. Your neutrons are still transferring kinetic energy into things.
So a meltdown is still a concern at that point, but you're not creating energy in the form of fission reactions at that point. And that's gonna buy you a lot of time to figure out another solution, essentially. And that's kind of a built-in safety mechanism, a negative void coefficient. So if you lose your coolant, you lose your moderator, you lose your fission, essentially. It more or less, and from the perspective of fission, it kind of shuts your reactor off in a lot of ways. You still got neutrons flying around, but we can deal with those in other ways. Now, I think now's as good a time as any to transition into the RBMK reactor. So the RBMK actually stands for something. Would you like me to tell you what RBMK stands for? I'm going to break out some Russian here. All right.
Is the first word Russian?
No.
R?
No.
Russian ballistic missile.
Actually, so for a So this is a type of reactor. The first word is reactor. So that's funny.
Okay.
But it's spelled weird because it's Russian. So here's sorry to any Russian folk at home here. Let me break out some. All right. RBMK stands for Reactor Bolshoi Mashknasti Kanalny.
Oh, obviously.
That's what it stands for.
I can guess that.
What that essentially means, I think that roughly translates into just like a high power reactor or something like that. It's another one of those not very helpful names, but it's in Russian, so it's interesting.
Maybe it's helpful for Russians.
Maybe.
I mean, if we knew Russian, I'm sure it'd make more sense.
Probably, honestly. So an RBMK is a type of boiling water reactor. We just talked about those. Don't you remember?
I barely.
So a RBMK is a type of boiling water reactor. These are not made anymore, and you're about to see why. So instead of water being your coolant and your moderator and having that built-in kind of safety mechanism of a negative void coefficient, everything is almost the same as from the kind of the perspective of the core, except that instead of water being a moderator, graphite is a moderator.
Right. Yeah.
Now, here's why that really matters a lot. So graphite is a great moderator, but here's the problem. If your coolant boils away, which can happen in a boiling water reactor, you still have moderation.
Which increases reactivity.
Which increases reactivity by slowing down neutrons. So in the event that you lose all of your coolant, you can still create fission events which release neutrons, which can still be slowed down, which can still create fission events.
Yeah.
And this is kind of a runaway situation. I don't know, kind of a runaway chain reaction. And there is not a lot to do with stopping that other than potentially scramming the system and just trying
dropping all the control rods.
Dropping all the control rods. So then what we would say about an RBMK is that it has a positive void coefficient. Now, if you've watched, this is one of the reasons why I'm really interested in the Chernobyl event, which we're about to get to. But if you were to watch the HBO miniseries about Chernobyl, the positive void coefficient they talk about that a lot. And what that means is we just talked about what a negative void coefficient is. A positive void coefficient is just simply the opposite. In the presence of voids, your reactivity goes up.
Which is much, much, much worse.
Which can be dangerous. Now, I have listened to enough nuclear engineer people, nuclear physicists talk about this, and they will all say that a positive void coefficient is not inherently dangerous. It's less safe in general than a negative one because that's kind of a built-in negative feedback loop.
Yeah.
But there are still reactors today that are being built that have positive void coefficients.
Really? Mm-hmm. Why? How is that? How could there be a coolant void with reactivity going up and that be a good thing?
I really wish I wrote this down. I'm trying to remember the type of reactor that I heard this guy talk about.
That seems, maybe this is just my ignorance about same situation about boiling reactors, rearing its head, but that sounds dangerous to me.
Well, I don't know if I'm going to be able to find what I'm looking for here in a timely manner, but I think ultimately the negative effects of a positive void coefficient can be managed with proper safety systems, which is obviously the case. Now, you would say, why just not have?
Yeah, why worry about it?
Yeah, and the best answer I can give you is there's probably a reason that I'm unaware of.
Surely, if positive void coefficient reactors are still being built today, then surely there's some engineering workaround that makes it, trivial.
But here's the thing. I mean, even considering that, the vast majority of reactors are going to be PWRs and BWRs, which have a negative void coefficient. Right. So on the large scale, for the kind of bulk of your energy production, we're going to be using something with a negative void coefficient for a kind of built-in safety system. Okay, so I mentioned it, and we're going to talk about it now. So the RBMK was the reactor used in the Chernobyl incident. So why talk about Chernobyl at all? Because you don't need to talk about Chernobyl in order to talk about nuclear power production. But here's the thing. We kind of mentioned it a little bit earlier, but perception plays a huge role in the public's acceptance of nuclear energy, right? And why it's not, other than cost, why it's not as popular as it maybe should be, if we're being honest. And
definitely should be more popular.
And one of the things that really impacts public perception is going to be nuclear weapons. That's going to be one thing. And just honestly, a general kind of distaste for the word nuclear. We were talking about that, I think, last night.
Right.
Let's just get a new
word is used for the most destructive weapon we have ever created, and also one of the greatest power sources we have. Right. And it's the same word, which is tragic.
Right. And then another one of these boogeymen of the nuclear sphere is going to be nuclear accidents. And the chief among them, the worst among them, is going to be Chernobyl. So I do we're not going to spend too much time on this because, I mean, we're just going to kind of go through some quick bullet points here. But I want to outline what happened, why it happened, and why it couldn't happen again. Before we get into the Chernobyl timeline, something I wanted to mention about the RBMK. So it actually had no kind of containment structure whatsoever.
Right. There is what you were talking about earlier. There's nothing around the core.
So you kind of you've got the core, outside. And then you've got the steel lid of it where all your kind of control rods are set. And you can actually walk on the top of it. It's very interesting. If I remember to, we'll throw up a picture of a non-destroyed Chernobyl reactor hall, called a reactor hall, where you can see on the floor all these like little squares where these all sit, and you can just walk right across it. It's just like the floor is the top of the reactor lid, if that makes sense. But no shielding beyond that, basically. And ultimately, that's going to be a cost
unsafe
thing.
Design. Yeah,
it is completely unsafe. No, that's one thing that people say about Chernobyl is that they, in general, had a lack of a safety culture. So that the not only was the reactor flawed in ways which we'll get into, other than just the positive void coefficient, but also in the sense that they did not have the proper shielding needed or containment that they needed, and also just the general operation was a little too lax, I would say. But okay, so the actual event occurred on April 26, 1986.
A couple days before my birthday.
Oh, wow. You were around in 1986 too? You were there?
Yep.
How old would that make you?
If I was born in 86?
Yeah. I was going to say old as frick, but that's really insulting to anybody that's that old. I was going to
say, not really. Like, freaking 40.
Freaking 40? That seems like so long ago, I guess.
Well, it's because it's 20 years before we existed.
Oh. I suppose you're right.
Or like 15.
So we're going to... The actual event that starts on the 26th, we're going to start talking about the 25th. And the reason we're going to start here is actually to highlight a really interesting point. So if you were to, let's say, watch the HBO miniseries or really talk to almost anybody that has a kind of baseline knowledge of Chernobyl, they might incorrectly say something to you. And they're going to say that xenon buildup from the day prior played a massive role in the explosions that occurred. And that's actually not the case. I found out. This is the really interesting thing that I learned.
Really?
Yeah. So let's walk through this a little bit. So where are we at here? At 1:06 a.m. the day before the incident. So this is the 25th. right in the morning of the 25th, they begin to reduce power in the reactor for a test that's going to occur. So the test that they're doing is to see, they're actually doing a bunch of tests, but one of the main ones is they're wanting to see that in the event of a reactor shutdown, is the turbines that are still spinning generating enough electricity to run the pumps long enough for the diesels to come online and take over that work for them. Does that make sense?
Diesels?
Like diesel generators.
Oh, okay.
So yeah, and I don't remember, I wish I'd written this down. The diesel generators, the time it takes them to kind of get up to speed or to start working was abysmal. It was like 40 seconds or something like that.
For a generator to turn on?
Yeah. Which in the world of, maybe it was 30, but in the world of nuclear energy, 40 seconds is a long time.
If you'll recall back to how quickly I said reactions can happen, these things are happening in fractions of a second.
Yeah. I think anymore, it's like maybe 5 to 10 seconds. That's like standard now. Yeah. But anyway, so the test that they're powering down for is to see that if in the event of a reactor shutdown, if the still spinning turbine is producing enough electricity to run the pumps long enough for the diesels to come online. Okay. So they're stepping things down periodically. So that happens at 1:06 a.m. And they're stepping it down because when you lower reactor power, xenon builds up. So, let me dive into that a little bit further. So, xenon is always being produced.
Yeah.
As a product of fission.
Byproduct. Yeah.
But here's the thing. When you're lowering reactor power, you are, let me see if I can wrap my own head around this. You are taking more fission events out of the equation because you have to have less of it in order for the overall power to go down. Therefore, the amount of neutrons available from fission is less that the xenon from previous fission reactions do not have the neutrons enough to burn off.
Oh, so previous xenon 135 offage from fission reactions, as it were, is remaining there unfilled by an extra neutron to turn it to xenon 136, making it benign. So it's building up of 135
because you have fewer neutrons.
Have less reactions, creating less neutrons to turn them into 136.
Now, granted, because you have less reactions, you also have less xenon production.
Right.
But you still have what was there, and it's going to take 9.2 hours for its half-life. Yeah. So I mean that's
on average. Interesting.
So the reason they're stepping this down periodically is to kind of step it down and then give kind of let everything kind of plateau for a little bit, give the xenon a chance to burn off. That's what they're doing, and they're doing that all the way down to, I want to say it was like half power. I don't know what that would be as far as megawatts go. Maybe like 700 to 800 megawatts, something like that. So around, that's a typo, around 2 p.m., not a.m., around 2 p.m., it is decided that the test that they were going to run maybe around 5 or 6, is going to be delayed because a nearby reactor facility, I think I wrote it down here actually. I think it was the South Ukraine. Yeah, the South Ukraine nuclear power plant had encountered an issue and it itself had scrammed. So they had pressed there in RBMK's. Actually, I don't know if South Ukraine was an RBMK, but anyway, in RBMK's, it's called the AZ5 button. So they had scrammed, and with it taking like 800 megawatts out of the grid.
Which is a lot.
So that's a lot of power. So then these guys are lowering power in Chernobyl Reactor 4, and they get a call on the telephone. And they say, you can't shut down the... What?
You got to call on the telly.
You got to tell on the telly. And they say, you can't shut down. We need all the megawatts we can get. Essentially. So they say, well, shoot. All right.
We just lowered the power of this son of a gun.
Yeah, we just lowered the power on this. So so this is now around, I think, 6 or 7. They raise the power back up. to I think like 1100. I want to say.
What's the maximum power capacity of the Chernobyl RBMK?
I'm gonna Google that because that's a really good question. I didn't write it down.
If 50% or whatever was like 600 or 700 megawatts, makes me think probably 1,500 megawatts is its total power capacity. But I don't know if it scales linear like that. I don't know enough about power production or watts production to know that.
1,600.
Okay, so yeah, it was okay about that. Interesting. So 1,600 megawatts power. That's less than that of modern reactors by quite a bit, ain't it?
Probably. I have no idea, but I wouldn't be surprised to.
Yeah, I'm not sure the max power output of modern nuclear reactors, which seems like a trivial thing to know. I'm surprised I don't know that.
Okay, so like I said, yeah, decide they're going to have to postpone this. This test was supposed to occur at like 5 or 6, something like that. And now they got to hold it. And they raise the power back up slightly, but not up to full capacity by any means. At 11:10, they get permission to actually run the test. So they start lowering the power. Now, the important thing to note here, I don't really know how much of an effect this had, because with all of the research that I've done into this, it kind of seems like the crew did everything by the book, but this at least
up to this point
and following, basically, well, for the most part, there are a couple key moments that were a bit whoopsie daisy, as we'll see. But with this delay, the test is now going to occur during the night shift. So this is important because the night shift is a less experienced crew. As a matter of fact, the person in the control room in the night shift that people are ultimately going to say blew up Chernobyl, and this is, I believe his name was Leonid Topkanov, was 25 and had only been unsupervised, untraining, running his control rod station for like 2 months at this point. Which is not a long time. So anyway, the night shift takes over. There is an unexpected power plummet at this point. So this is crazy. I wish I understood this a little bit better. A lot of the events of Chernobyl are a bit either controversial or unknown, just because there's not a lot of data. The computers that they're running at this point in time are pretty dang primitive.
Yeah.
And there's a lot of delay on the actual output that they're going to give you as far as information goes. But power plummets at this point. And people say that it might have plummeted all the way down to around 30 megawatts.
So
which is
insignificant.
Which is practically nothing. I don't know if that actually was read out somewhere as far as on data, but it was around there. It was practically nothing. So they're faced with a decision here. This is Topkanov, and the other more experienced guy in the room is, I believe his name is Yuri Tregub, are kind of standing around the control rod station with a choice. And the choices are, they either shut down the reactor because it's practically dead anyway, or with what little reaction is left, try to raise the power back up. And that's what they ultimately decide to do. Now, the interesting thing about that is that was actually kind of the correct decision. You would think that you should probably stop.
Right. If there's an unexpected problem that you didn't know why it happened, I feel like raising power would be the last thing you want to do.
So they end up raising power, and they raise power. They can only get it up to about 200 megawatts.
Why was raising power the correct decision?
Trying to remember.
If that's by the book, then I feel like the book is a bit wrong or incorrect. I can't. Not that I know anything about this.
I can't remember what. I didn't write this down. I can't remember what. I think it might have been the actual like RBMK reactor manual. So theoretically, it was correct by the book, but the book was stupid.
Yeah, that sounds to me like the book was.
There is part of that. I think the point of that is that this isn't an operator error yet. It's more of a kind of design error or a rule set error. But I mean, correct me if I'm wrong, nuclear engineers out there watching this. Maybe that is just the actual correct decision, and has nothing to do with Soviet design. But they raised the power back up, and they can only get it up to about 200 megawatts. And the reason I talked about all of this is because xenon is not actually playing a huge role up into this point. We had the original power drop and the xenon buildup, but then we raise the power back up gradually, and xenon's no longer a factor.
What caused the initial drop in power? Was that xenon buildup?
The one where it got all the way down to like 30?
Next to nothing, yeah.
I don't know.
Is that known?
It might be. Man, hold on.
Because that's a pretty. If that's the sort of instigator of this whole thing, I feel like that would be pretty. But I don't know if xenon could cause such a dramatic shift in power level like that on its own. I don't really know enough about quantities of.
Well, it depends on. Well, I mean, it can pretty much halt reaction because it's taking away all your neutrons, so you can't. Yeah. But if
reaction halts, so does production of xenon 135.
Mm-hmm.
So eventually it would. I mean, it might halt it to a stop, I suppose, if there's an equal amount of xenon and also uranium 235.
So this just says for the test, the reactor should have been stabilized at 700 to 1,000 megawatts prior to shutdown, but possibly due to operational error, the power fell to about 30.
So I guess so that could mean almost anything.
So that maybe that is kind of an unknown thing.
Interesting.
Yeah. So like I was saying, xenon is not playing a huge role up until this point. It does kind of play a role now in the fact that they can't. Because power dropped so drastically, now there is some xenon buildup in the system. And that's making it very difficult to raise power back up. So you have to, because xenon it's not just kind of a universal constant in a reactor. It kind of is in different places as far as in its gaseous state in different parts of the reactor. So you have to then pull control rods in specific areas of the reactor so that this xenon can burn off, if that makes sense. So they're having to, one by one, so Tregub and Topskanov are pulling the control rods kind of systematically in very careful positions in order to raise general power, and they get it back up to about 200 megawatts. Now, all of this time, there is... I think I wrote it down here. Steam. There's a lot of pressure happening in the steam separator. So the controller of the steam separator ends up lowering the pressure so that there is not this kind of coolant feedback collecting water that is already kind of heated. So by the time they stabilize back to 200 megawatts, the controller of the kind of coolant flow ends up bringing in feed water from like the external source into the reactor, so at the bottom of the reactor. So why this matters? So this matters because the coolant that is kind of cycling through the system is already pretty warm, and the feed water is, I think, like half of the temperature, roughly. So when it is pumped through the system, it is taking longer to boil, so it collapses your voids. You kind of conceptualize that.
Yeah, voids.
Yeah, the water that is cycling through the system naturally is already kind of heated, so you're creating voids at a consistent rate, essentially. If you bring in your feed water that comes in, now this water is not boiling nearly as quickly, and the voids collapse, decreasing reactivity, right? Because now your feed water that's acting as your coolant, there is not as many voids, therefore it is absorbing more neutrons, right? Because that is a factor here. So it's absorbing more neutrons, and your reactivity goes down. Here's the problem. In order to counteract the negative reactivity from your feed water acting as your coolant, the control rod operators are now pulling more control rods in order to compensate.
Okay.
And so this happens systematically. And then at some point in time, this is crazy. So this now is cycling through the system, and the coolant is heating up as it's cycling, as they're raising power, as they're pulling control rods. And it gets to a point where the coolant temperature at the bottom of the reactor is maybe a degree or two less than boiling.
So on the precipice of boiling.
Yeah. The water at the top, which is at the boiling point or boiled, it is only a degree or two less at the bottom, this is a big problem. Now here's the thing. For the test, I guess before I go to that, let me mention this. A lot of people will say that there was a power surge prior to scramming the reactor. I don't actually think that that's accurate. I saw a graph at one point in time. There was a slight uptick, which I think the guy that I was watching talk about this, he kind of correlated that to just kind of a margin of error as far as like the needle of the recording device kind of just vibrating, the pen vibrating. Because so compared to what was about to come, this is a insignificant power increase. But for the test itself, they have to shut down the reactor, like I said, for the turbines to spin down and to power the supply power while the diesels are coming online. So they hit the AZ5. This is the reactor SCRAM. Now, here's a quirk about RBMKs, and you already know this. But this is the ultimate thing that makes RBMKs so incredibly dangerous, is that the tops of the control rods, or the tips of the control rods, I say tips, it's like 6 inches of this stuff.
Yeah, it's a little fraction of the end of the control rod.
Well, no, it's huge.
Isn't it?
So,
it's huge?
What we're talking about is
compared to the size of the control rod?
I don't know the size of the control rod, but I can tell you that the graphite tips are about like 6 inches, which is big, which is very big. Well, anyway, so what we're talking about here is we mentioned that the RBMK uses graphite as a moderator. This is to slow down the neutrons to increase fission. Now, the control rods are meant to remove neutrons from the equation, stopping fission. Mm-hmm. But the tips of the control rods in an RBMK are tipped with graphite. Now, the reason for this is it's to displace the water as you are heading into your bottom pooled coolant at the bottom of the reactor. It's supposed to separate that out. Now, are there better choices to do this? There are. And there were actually many different proposed ideas for what could change as far as reactor design to remove the graphite from the tips of the control rods, but they just didn't do that. I don't know why. Soviets, money, communists, whatever. bunch of dumb commies, if you ask me. But anyhow, the tips of control rods are tipped with graphite, and they hit the SCRAM button, which lowers the control rods into the system. I the other quirk about RBMKs is that the control rods lower very slowly. This is not, I mean, with any sort of mechanical movement, it's not going to be near instantaneous, but in a lot of reactors, it's pretty quick. These are several seconds of lowering.
Well, it's basically as quick as gravity.
Right.
Will get it now.
Yeah.
As far as I understand.
But this is not the case for the RBMK lowering into the reactor. There was also, I read some speculation that the control rods might have also jammed halfway through.
I've heard that.
I don't know if that's the case. I don't know what the evidence for that is, but if that was the case, it makes it all the more worse.
Right.
Because why? Well, because now your graphite is now more kind of central. Not only is it more central, but the part that you want, which is the boron absorbing the neutrons, is now less in the system than in the graphite is.
Right.
Which is a big problem. So suffice it to say, you've got graphite at the tips of your control rods that are now lowering into the system. What this does is momentarily increases reactivity, which increases fission, which increases temperature. Now here's the problem.
our coolant at the bottom of the reactor is like a degree or two below boiling. And you see where I'm going with this.
Yeah.
So the temperature increases, all of the water at the bottom of the reactor instantly flashes to steam. Comes shooting up through the reactor vessel and pressing up against all of the steam is all of the emergency like steam escapes are all going out of that, but there's still too much pressure, and it ends up blowing the lid off of the entire reactor core. Sends it flying up, and then it comes back down, and that's your first explosion, a steam explosion.
Yeah.
Now, I don't know much about hydrogen explosions. I don't honestly know much about them, but I know that with the now exposed reactor interacting with what water was left in the system, there is now a hydrogen explosion, which is a bigger explosion.
Yeah.
That just sends so much reactor debris and radioactive material up into the surrounding environment. As well as there was the graphite used as a moderator began to smoke. Essentially, kind of the graphite itself was on fire, and there was a graphite fire.
Yeah, which is a bad fire.
Which is really bad. There's about 1,000 things we could talk about as far as the effects of Chernobyl, but we really don't have a lot of time to do that.
Why is xenon I heard of this as a xenon issue, a xenon buildup neglection, basically.
So I think when people think about that, they're thinking about all the xenon builds up from the day before, which is not the case. Because like I said, if I can find the graph, we'll maybe throw it up on the screen. But you can see xenon buildup all the way through the day before, but then it's burnt off because it's held at power and then raised power.
Yeah.
So by the time the test actually starts, xenon is almost a non-factor. Now, where xenon is a factor is the fact that the power drops so quickly, all the way down to 30 megawatts, that there was xenon buildup at the bottom of the reactor at that point in time. Why that matters is because the pulling out of control rods to compensate for that. So you have very few control rods in the reactor at this given time. And that is going to cause a problem whenever you're now pumping the feed water. And we talked about the whole heating of the feed water loop and all of that and degrees in reactivity. So by the time that you actually get to the point where the water flashes into steam, there are hardly any. I think they said like 7 control rods. I think it was the final readout. Was like 7 control rods in this array of I don't know how many. I don't know how many. I know that the minimum is like the absolute minimum is like maybe 15 or 20.
Nice.
So that is like
they already blew past that.
That is I think if you get below like I think it's like 14 or 15. If the readout says you're that low, you have to immediately shut down the reactor. Which of course at this point it was too late.
Yeah.
Even if they did,
because they're
that's
too slow.
That's essentially what they did. As shut down the reactor for the test. They didn't do it because of the operating reactor margin, which is the kind of readout of equivalent control rods in the system. But yeah, no, that overall kind of coolant loop thing was definitely made worse by the xenon buildup because they had to pull out so many control rods to compensate.
I see.
But here's the good thing. Here's the good news. That was all scary stuff. Here's the good news. Something like this could not happen again.
Right.
It takes
because that's a stupid reactor design.
Well, so that's one thing. RBMKs are no longer built. So there are reactors with positive void coefficients, but they're not as common. They're in very specific types, and they are very heavily regulated as far as like safety systems and safety redundancies. And we don't use, I don't think very much at all, graphite moderators. I don't believe.
Well, it just makes to me more sense to use water as a moderator.
Right.
Because like how it's so much more safe to where if your moderator all of a sudden goes away, which also happens to be your coolant, it makes just so much more sense for that to decrease reactivity as a safety precaution.
Yeah, so we don't build reactors like that anymore for the most part. The other thing that we're going to have now that an RBMK didn't is a very robust containment building. So like I said, there was hardly anything to stop. Even if we pushed a reactor to this point today, which couldn't, but if we did, these containment buildings are built to withstand internal explosions.
And also an airplane.
And potentially even a missile. Like it's, you know, it's just like...
These can't, even if everything goes wrong, these things can't go that wrong.
Yeah. And the other thing, so I didn't really touch on it too much when we were talking about the events of Chernobyl, but systematically throughout the night, they were disabling safety systems. Whether that be the automatic water filtration system to kind of cool the reactor core. Now they turned that off because they didn't want it interfering with the test. And there was a couple other. There was this hilarious quote that I saw on one of the like forums that I was reading, and they said the computer told them to shut off the reactor, so they shut off the computer. Is essentially what happened.
Nice.
They were disabling safety systems so that they could do this test in unsafe parameters. Really.
Well, they got them.
You can't really do that today. There are so many redundancies. There's so many authorizations that need to take place that you can't just say frick it, we ball, and turn off all the safety systems.
Safety precautions.
Right. And this is maybe one of the biggest things, alongside the use of reactors with negative void coefficients. We don't tip our control rods in a moderator substance. We just don't do that.
Right.
Because that's stupid.
Yeah. Why would you? That's like freaking, I don't know. I can't think of a good example. That's like lacing a Carolina Reaper with hot sauce. What are you doing that for?
That's
making something worse.
That wouldn't be good, would it? So that's fission. I mean, like I said, there's about 1,000,000,001 things that we could talk about and still be in the realm of fission. But I think for today, that's good enough. Like I said, I mean, we walked through kind of how fission works, kind of a good surface level understanding of how that works. What you're going to be looking at when you look at the operation of a nuclear reactor, and then the worst nuclear disaster in history, and that being Chernobyl, and how it cannot happen again.
And also, I would like to note, as far as deaths per megawatt generated, which is how you would standardize the safety of something like power generation as a career, nuclear is like fractions of deaths per megawatt generated compared to gas, coal, and fossil fuels. Like it's way more safe.
Well, even, again, we just talked about Chernobyl being the worst disaster in history. I think the death count on that officially is under 100.
Which is nuts, because there's been singular disasters of like, even something like a hydro dam breaking has resulted in way more deaths than that.
Yeah.
And that's a renewable source too, which, I mean, that's the gold standard of energy, is a zero waste way. But even then, safety, as far as safety is concerned, nuclear is pretty much unbeaten, unless it's like wind turbines. Those are pretty safe. Not for birds, but for us,
the birds are kind of fricked.
Yeah, they get freaking whacked with a baseball bat, basically.
Yeah. Well, so all that to say, if dummies like us can kind of a little bit on the surface level understand it, anybody else can understand it. And it doesn't take a lot of knowledge to really look at this and say, you know what, this is clean. This is relatively safe relative to other forms of energy production.
Right.
It's expensive as all heck. I'll say that.
Right. There is not perfect. This is not a silver bullet of energy generation. It's one of the problems of fission plants is they are billions of dollars to build, and also they take a freaking long time. If you were to invest in a nuclear plant as a form of power, it might literally be a decade from deciding to build it to it generating power for the grid. Yeah. And that's a lot of money to be spending and a long time to not see it coming back.
Yeah.
So there's that, but there's also the problem of the fuel for these reactors is the same fuel for bombs. So uranium, when I was talking about earlier about enriching uranium, in a reactor, the uranium-235 to 238 ratio can be as low as like 3.5 to 5% uranium-235. In a bomb, that needs to be like 90% uranium-235, because in a bomb, you want the reaction to happen as quickly and as much as possible. And the way you do that is by mashing as many of the 235 isotope uranium as together as possible in a bomb. And enriching the uranium is a very, very human process. You're not going to just find enriched uranium, under your backyard. So in the event that we want to build more bombs, what we could do is just go to the nuclear plants and get some of that enriched uranium, enrich it further, and build bombs with it. That's a downside, is the fuel to get these plants up and running can also be, in the event we want to build more bombs, just used for the bombs instead. Yeah. That sucks. And that's next episode. We're going to talk about fusion. That is a problem that cannot be the case with nuclear fusion. Mm-hmm. But yeah, so it's not a magic solve all your problems power source, but it's way better than what we're doing right now.
Right.
So yeah, I'm about to get quizzed.
You're about to get quizzed, dude. I'm telling you, man, between what you didn't know and you just learned and what you already knew, you're probably going to get all of these.
All right, let's see if I can clean sweep this quiz.
Here's what we're going to do. So I have multiple choice questions for this. I'm just going to ask you the question. If you get it right with before
the multiple choices are presented.
Yeah. If you can just answer it off rip, I'll give you 2 points. If you need the multiple choice and I'll give it to you and then you get it right, you get 1 point.
Okay.
Let's see if you can clear 15 points.
Out of how many questions?
10 questions.
Okay.
So at least.
Okay.
So you need,
damn. Okay. So I need to clean sweep this and also get half of them without the multiple choice presentation. Okay. Holy.
And
that seems tough for me.
In hindsight, maybe that was a bit unfair, but I've already said it.
Okay.
And
15.
There's no possible way I could go back on that now.
No possible way. Okay.
I mean, it's about as sure as anything, really. Yeah. Okay. This is question 1 here. Most large-scale electricity generation methods ultimately rely on which basic process?
Most large-scale energy production methods
ultimately rely on what basic process?
Most large-scale energy production methods?
By percentage.
A chemical reaction by way of either burning coal or fuel or gas.
What do they have in common to produce energy?
The generation of heat by way of burning reactions, generating steam.
There you go. Okay, that's what I was looking for. The correct answer was heating water to produce steam to turn a turbine.
Oh, yeah. Okay, yeah.
I was like, we'll get there. Anyway, approximately how many neutrons are released per uranium-235 fission caused by thermal neutrons?
2 to 3.
Yeah, that's correct.
2 point something.
So 4. Yeah, 2 to 3 was the answer.
Yeah. Okay. Did I get the first one?
Yeah, you did.
Okay.
Making sure. Hold on. This one's a little weird. Okay, I don't know if this will work for my don't have to get multiple choice for 2 points thing, but we'll see.
Okay.
The question is, as I wrote it, is simply a fission chain reaction can only occur if blank.
Whoa. Whoa. Okay. A fission chain
that really works with this.
can only occur. Well, let me just rattle off what needs to happen for a fission chain reaction. It can only occur if 1, you have enough uranium that is 2, enriched to be at least 3.5 to 5%, 235, and also 3.
I've made this difficult for you, haven't I?
Yeah, I mean, you need plutonium usually to get it started, or California.
California. Well, you've got it right already. The correct answer I had was enough fissile material exists in a confined space.
Okay, so yeah, the proper ratio of enriched uranium.
Yeah,
basically.
you got it right.
Good.
Why is xenon 135 significant in reactor operations?
Because it can absorb one of the neutrons that would otherwise be used to collide with a uranium nucleus.
Correct. I just said it is a powerful neutron absorber.
Yeah.
Yep. And everything that you just said is also a part of that. What is the approximate half-life of xenon 135?
Like 9 hours, 9.5 hours about.
I'll give it to you. 9.2.
Okay.
That's approximate. Thermal neutrons travel at approximately what speed?
Couple kilometers a second. Like 2.5 or so.
2.2. I'll give it to you. That's fine.
I'm hovering around it.
Yep.
I suppose.
The primary function of a moderator is to what?
Slow down. Well, convert fast neutrons to thermal neutrons.
Correct. Slow neutrons.
Slow them down to increase absorption of uranium.
I don't know what score you're at, but you're winning.
Okay. I haven't yet needed to be presented with the multiple choice, so this is good.
Yeah. Why is a negative void coefficient considered a safety feature?
Because as the voids are created, the reactivity goes down, which is safer than it going up.
Yeah, I said it causes automatic power reduction.
Yeah.
Or it describes automatic power reduction in the presence of voids, which is essentially what you said. Okay.
What am I at here?
Well, I'm about to ask you question 9. So you've answered correctly without multiple choice 8 questions, 2 per. So I'm
at 16.
You've won.
I've won. Hey, okay. Dang. That's great. I'm blasting this game.
All right. Why did increased cold feed water initially, this is for Chernobyl, why did increased cold feed water initially reduce reactor power?
Frick.
That one's a bit tougher.
Initially reduce reactor power. I need the multiple choice for this one.
Okay. Did it?
I don't know how to. Yeah.
Did it A, increase neutron leakage? B, collapse steam voids and increased neutron absorption? C, cooled fuel rods below critical temperature? Or D, cause control rods to insert?
B, collapse steam the voids.
That's correct. That is correct.
Creating more absorption. Yeah.
Once you get the multiple choice, it's pretty easy.
That one. Yeah.
All right. What caused the final rapid power spike after the shutdown button was pressed?
What caused the final rapid power spike? The complete evaporation of all water. Right? And as well as the graphite tipped control rods.
There you go. I was like, what caused the flashing to steam was there you go. The graphite tipped control rods. That's what I was looking for. Well, you got all 2 for except 1. So what would that be? That's 19 points?
Yeah, out of 20.
That's pretty good.
That's pretty good. I know nuclear on a basic surface level now.
Well, I'm curious. Anybody watching this, let us know kind of what your perception of nuclear is.
What did you think about nuclear power generation, or did you even think about it at all? Because that's also
if you thought about it prior, what was your thought process? Knowing, hopefully, there's something to take away here. What have you taken away, and does that change your ultimate perception of it? And are you kind of maybe excited for the kind of nuclear future that we're hopefully moving into?
Yeah, one would hope. And like I said, next episode we're talking about fusion. Fusion generators don't exist as far as generating power for our grid yet. So that'll be a more current events type episode, but it's going to be fun because if you don't know, fusion is what powers the stars, and we're going to use it.
That's pretty cool.
We'll talk to you then.
See ya.